Hello everyone, this is another video that I just created for the linear regression model and how we can develop it. First of all, I will go through the introduction to linear regression and I will explain for you the mathematical foundation of linear regression model, what are the assumptions that we should consider and how we evaluate the model, and finally the applications that I will explain them in the form of examples. First, linear regression model was a classical statistical model that helps us to understand the relationship between variables. It just models the relationship between the dependent or target variable and the independent variables or predictors. The second characteristic of the linear regression model is that when we use a linear regression in the form of machine learning, it is accounted as the supervised learning model. And we use labeled data that include the input variables plus the known output or the labels to train the algorithm. The third one is just helps us to bridge between the statistics and machine learning. So in detail, we want to see what is linear regression. Linear regression is a supervised learning algorithm that is one of the most fundamental and widely used algorithm in supervised machine learning. We already know the correct output, that is the target values or the target variable, and the model just learned the relationship between the inputs and outputs. What is our purpose? Our purpose is to learn and find a mathematical function that can accurately predict the future values or future outcomes using the labeled data. You remember this diagram that I used it for the supervised machine learning model, and we have the labeled data, and including the in the form of input raw data and the labels, and the supervised machine learning models acts like a supervisor that get the training data. That use this labeled data to train the algorithm and according to the desired output, and then use this trained algorithm on the test data or on scene data to predict the labels or outputs. So in the linear regression model, exactly like I explained in the supervised machine learning, if we want to use it in the machine learning framework, it works like this. What is linear regression and the second characteristic of it? It is used for predicting continuous values. We know that if we have numeric values, we should use regression models. So if we have continuous values, we should have linear regression models. And if we also have discrete values, we can use linear regression models, but the type of linear regression model is, different. That I will explain in one of the example if we go ahead. So linear regression is specifically designed for regression problems, and especially the target variable should be continuous or numerical. Examples of continuous predictions such as houses prices, patient pressure levels, or predicting the cancer tumor size, or predicting the temperature, or income, individual's income. Now, if I want, now I want you to pause your video and just read all of these examples and to see whether you can use linear regression or not. This is very important that in the first step, you can distinguish whether you can use a linear regression or not. So, for the first problem is that we want to predict a person's annual income in dollars using years of education and work experience. So what is our target variable is predicting the annual income in dollars. It is a continuous variable, a numerical variable. So we can use linear regression. For the second one, we want to predict whether a patient has diabetes based on BMI and age. So it doesn't matter how many and which predictors and features we use, but it matters what type of variable we use for our target variable or our dependent variable. Here, we just want to predict a patient whether he or they have diabetes or not. So it is a classification problem. Because we want to see whether the result of their diabetes experiment or their diabetes is yes or no. So we cannot use linear regression in this problem. The third one, we want to predict the student's final exam score using hours studied. So hours studied is a feature. So we want to predict final exam score. So final exam score here is a target variable and it's a continuous numeric variable. So we can use linear regression. The fourth one, predict whether a tumor is malignant or benign using tumor size. So we want to see whether the tumor is malignant or benign. So we have two classes here. So it is a classification problem and we cannot use linear regression. And the fifth one is predict house price in dollars using a square footage and number of bedrooms. House price in dollars is our target variable, so it is continuous numeric and we can use linear regression. The sixth one is predicting blood pressure using age and weight. The blood pressure, again, is a continuous and numeric variable, and we can use linear regression. And the seventh problem is predicting the name of the region based on income level. Name of the region. Even if you use number representations for name of the region, since this is, different classes and we have multiple classes that we want to predict, we cannot use linear regression. It's a classification problem. And number 8, predict the number of hospital days using age and diagnosis severity. Number of hospital days. You may say that number of hospital days is numeric, but it is not continuous, it is discrete. We can use linear regression, but maybe the type of linear regression that we use, maybe it should be Poisson regression. And the ninth one is predict whether a person survives a disease using treatment type. So whether a person survives as a disease or does not survive a disease. So we have two classes again. It's a classification problem and we cannot use linear regression. Here you can see also the responses. Now, we understood that linear regression models the relationship between dependent and independent variables. But what are dependent and independent variables? Dependent variables are the output or target variable that we want to predict, and so their values are dependent to the features or independent variables. So independent variables are features or predictors. These are the names that we can use for each of those interchangeably. And this is important to learn them because you may see different names in different papers, studies, or in different places, and it's better to be familiar with them in advance. Here now, I put another practice for you. Please pause this video and see whether you can answer these questions or not. So for each question, you should define the dependent variable and independent variable. For practice 1, we have a hospital collects weekly exercise hours, age, cholesterol level, blood pressure, and whether the patient had a heart attack. It means it has a heart attack, yes, or it doesn't have a heart attack, no. So the researcher wants to study whether exercise predicts heart attacks. So what is our target variable here? Whether the patient had a heart attack, yes or no. So this is a classification problem. And what are our predictors? A hospital collects weekly exercise hours. So weekly exercise hour, age, cholesterol level, blood pressure are our independent variables. Can we use linear regression for this problem? No, because our target variable is presents that our problem is classification problem. We want to predict the classes. Now, if we want to come up to the practice too, consider that a university collects hours studied, attendance rate, major, high school GPA, and final course grade. The dean wants to model academic success. Which of these variables can show the academic success? Only the course grade. Here, because we recorded the courses like A, B, C, D, F, or EF, it means that we do not, we do not have continuous and numeric variable here. And so here again, we have a classification problem. This is our dependent variable, and others, including our hours studied, attendance rate, the major, high school GPA, are independent variables. So we cannot use linear regression. Here is the response that you can go through it and check your results. Now we want to know what are different types of linear regression models. The first type of linear regression model is simple linear regression, which is the basic form of it. We use it when we have just one independent variable, x. And so we use just one coefficient, beta 1, and the intercept, beta 0. And also we have one dependent variable, or y. What are the examples? For example, predicting the population density using only the rate of births. Predicting the rate of lung disease mortality using the only concentration of PM2.5. Predicting the mortality rates using all the mortality rates using access to healthcare centers. The second one is multiple linear regression. It is used when there are two or more dependent variables, but we have, again, one dependent variable. So we have multiple independent variables and just one dependent variable. For example, we want to predict the population density using rate of births, rate of deaths, and urbanization level. For example, we want to predict the lung disease mortality using the concentration of PM2.5, age, rate of cigarette smoking, industrial emission, radon exposure, and others. We want, for example, to predict the mortality rates using access to healthcare centers, age, and income level. The third type of linear regression model is polynomial regression. We use when the relationship between x and y, or independent and dependent variable, is nonlinear, but still we model it as a linear regression by adding polynomial terms. This is polynomial terms. It means we just give it power. You may ask that, do we account polynomial regression as a linear regression model, as one type of linear regression model? Yeah. We should consider it as one type of linear regression model. Why? Because in the explanation of linear regression model, we should have linear coefficients. Okay, it doesn't mean that we should have always linear terms. So we can use polynomial terms. in the linear regression. For example, prediction of population density using birth rate squared, death rate, and urbanization level. So the population can grow faster at higher birth rates. It means we should put power for the birth rate as a independent variable. Or predicting lung disease mortality rate using PM2.5 power 2, age power 2, and smoking rate. But the mortality may increase faster at higher pollution or older ages, at higher pollution or older ages. So we have power 2 for both of these independent variables. And prediction of mortality rate using income, power 2, age, and access to healthcare. So mortality may decrease quickly at low income levels, then change slowly. And another example, predicting hospital visits using temperature, power 2, and air pollution level. So visits increase more during extreme temperatures. The fourth type of linear regression model is multivariate linear regression. When we want to predict multiple target variables or dependent variables based on the same predictors. For example, we want to predict lung cancer mortality, chronic respiratory disease mortality, and cardiovascular disease mortality using concentration of PM2.5, urbanization level, and forest cover. Now, we again come to time to practice. We want to know which type of linear regression should model for each of these questions. Please pause your video and explain for me. Question 1. Predict blood pressure using age. As you see, we have a simple linear regression. So predict blood pressure is, blood pressure is a dependent variable and age is an independent variable. So for question 2, predict electricity consumption using temperature, assuming the relationship is curved. When we say that assume that the relationship is curved, we should use polynomial terms. So this is the polynomial regression model. And in question 3, predict crop yield using fertilizer amount, where yield increases, then decreases, increases, then decreases at high levels. So again, we should use polynomial terms here. This is a polynomial regression. And predict a stroke and cardiovascular disease rates using income level, rate of cigarette smoking, and population density, since we have two target variables. But again, the same predictors, we should use multivariate regression. And I just want to, I see a typo in my question. It should be which type of linear regression model should we use in this question for you to prevent confuse. This is the results that I provided for each question, and you can check your answers and results with this slide. Now, it is very important if we want to develop a linear regression model to follow all of the assumptions of it. So what are the assumptions of linear regression? The first one is linearity. The second one is independence. The third one is homoscedasticity. The fourth one is normality of residuals. And the fifth one is no multicollinearity. That I will explain each for you completely. What does linearity mean? It refers to the relationship between x and y. So it doesn't mean, for example, not whether the equation looks simple. So the expected value of y given x should be a linear combination of the predictors. So it doesn't mean that the relationship, as I explained before, must look like a straight line. It doesn't mean that no curves are allowed. So we are allowed to use curves. Each predictor contributes additively to the outcome. Additively to the outcome. The change in y or dependent variable for one unit change in x should be a constant. It means b should be a constant. Linear means that the b shouldn't, for example, like polynomial terms or polynomial or other, I mean, multiplied by each other or some other operations. And we cannot apply some other operations on them. They should be constant. So no multiplication between the coefficients and no nonlinear functions of the coefficients. If you want to, for example, if you want to search for further readings in the linear regression that you want to completely learn about it, you can use the linear regression book, which is authored by Douglas C. Montgomery. It's an introduction to linear regression. It's a full guide for you to learn the whole linear regression models and their mathematical formulations. The second assumption is independence. What does independence mean? Observations should be independent of each other. So, you may ask how we can understand that the observations are independent of each other when the error terms are independent each other. There is not any autocorrelation between them. So our one observation does not influence another, and the covariance of for example, the error which is produced by developing the linear regression model for one observation should be, against another observation. The error of another observation should be zero. So this is very important. So if we have time series data, we know that in the time series data, each observation is dependent to the past observation, to the previous observation. And so it means that there is some autocorrelation between them, and we cannot use linear regression models. Another type of, data sets is just using when we just repeat the measurements, for example, for some individuals. We just, for example, collecting data for one specific or similar individuals at different time steps or at different occasions, and this means that there are some autocorrelations between our observations. And the third one is clustered data. When we are just collecting data, for example, from students within same schools, in each school, students share similarities. So there is probably a autocorrelation between them, between the observations. And especially for the spatial data, as we know that the proximate regions influence each other. So we have a spatial autocorrelation, and we cannot use linear regression always. Another assumption that we should follow is if we want to use linear regression is homoscedasticity. What is homoscedasticity and what does it mean? It means that the variance of the error terms is constant across all levels of the predictors. So the spread of the residuals remains the same for all values. So if the error variance increases with the x, or with the observations, it means that we do not follow we have heteroscedasticity. Or if it decreases, we have heteroscedasticity. So it is important that we have constant variance with increase of the independent variables for the residuals. This problem can be solved by standardizing the variable. Maybe we use different variables and different features in our data set that they have various scale. For example, we may use age. And we may use, for example, the temperature. We may use, the mortality rate of, for example, cancer, and all of these features, are measured in different scales. So, if we want to follow the homoscedasticity assumption, we can just standardize all of them and put all of those variables in the same range, and then, start developing the linear regression models. Here is just the example of the homoscedasticity and heteroscedasticity. And as you see, by increase in this picture, by increasing the, in the independent variable or x, the variance of, or the spread of, the difference between the actual values or and the predicted values, or the error terms, did not change. And is constant. But here in this example, which shows this heteroscedasticity, the variance is just changing by increasing the independent variable. Another assumption is normality of residuals. It is very important because when we want to generate and develop a linear regression model, we use hypothesis testing. We just, find confidence intervals for all of the coefficients and, find the p-values. So it is important that our data set, follow the normal distribution. And how we can understand that? By, investigating the distribution of the residuals. And so if we create a histogram of our residuals and we understand that it follows a bell shape, or it has no bias and not any skew, it means that they follow a normal distribution. For example, with a mean of mu or variance of sigma dou. That according to this, we can, go and develop the linear regression model. Another important point here is that you may ask that, for example, how we can understand that our residuals are normal. If And how we can, before, developing the model. It's not like before developing model, you can develop the linear regression model and then test the residuals. And if you see that they did not, follow the normal distribution, then they should use some other methods to make them normal. For example, to make your variables normal. And, for example, log transformation, which is a very, popular method in this region that you can use for normalizing your variables. Another assumption is that it is very important that if you want to develop a linear regression model, your variables should not have any multicollinearity. What does multicollinearity means? That it means that two or more predictors are highly correlated with each other, and the correlation between them, for example, is more than 0.5. So it means that predictors contain overlapping information, and one predictor can be explained by others. What happens if we use, multicollinear data set, and all of the variables have a correlation with each other? When we use this data set, the coefficients become unstable. What does it mean that the coefficients become unstable? It means that, for example, for one observation, we have a set of coefficients, and for other observations, we have another set of coefficients, and it is not generalizable. The model is not generalizable. So the standard errors are also increased, and the p-values are unreliable. And so the model will be hard to interpret. It is very important to remove the multicollinearity. How we can remove the multicollinearity? We have different methods. One of them is just remove the very high correlated, variables. If some variables are very high correlated, it means, for example, the correlation coefficient is more than zero point 0.5, 0.9, it means that they can be replaceable by your target variable. So it's better to remove them, to remove some of them. And also another metric that is very important to measure the multicollinearity and remove the multicollinear variables is variance implemented factor. It means that when you have the variables that have a higher correlation with each other, your variance is just implemented significantly, and you probably these VIF for those variables are more than 10. So you can remove the variables that they have VIF more than 10 to address the multicollinearity. But another important point here is that you may say that if I remove some of those variables, I may remove some of the important features, and maybe my model will not be very explainable. Is a very good fit of my variables. What should I do now? We have another, method, which is called principal component analysis, that you can combine, different groups of variables into one variable. And, by these principal component analysis, you just you know, reduce, this multicollinearity. And however, PCA also have its own challenges, and it is not very interpretable. Uh, in this case, some people, instead of using PCA, use factor analysis, or group-wise factor analysis that is more interpretable. If we have time, we will explain about the PCA and factor analysis, and in the future, and I will provide you with a video for that. Now, if we want to develop a linear regression model according to its statistical, perspective, we have three methods. The first one is forward selection, the second one is backward elimination, and the third one is a stepwise selection. That I will explain all of these, methods, and you do not need to do them manually, but it's better to know what's happened in these, approaches, especially most of the statistical softwares such as SPSS and Minitab use these methods to generate and develop a statistical model. The first one is forward selection. In the forward selection, we start with the null model. It means that we do not add any variables, and we just have the target variable or independent variable. So test each predictor individually and add them individually to our model. By adding them individually to our model, we just, after adding and creating a very small model by each of them, we evaluate the model using AIC, or archaic information criteria, that I will explain this in the future slides for you. Just I want to add that if the AIC is lower, our model is better. So by adding these variables, add the best predictor and choose the predictor that gives the lowest AIC in the first step, and repeat the process at the second variable. And finally, we repeat all of these steps. And in each step, evaluate our model using AIC until no improvement occurs, and until, for example, our AIC does not, reach a better amount or reach a better measure, and or we do not have any remaining variable. Here is the schematic picture of, the forward selection method that I explained for you, that you can focus it on, focus to understand better. The second method is backward elimination. So in the elimination, in contrast to the forward elimination, we start with a full model that we have all the predictors and just remove one predictor at a time and compute again AIC for each reduced model and choose the model with the lowest AIC. So we repeat all this process, all these steps until remove any variable that increases AIC. Or we could create a best model. Here is again the schematic picture of backward elimination that you can focus it on more on understanding backward elimination better. And the stepwise is the combination, a stepwise method is the combination of backward elimination and forward elimination. By first, in the first step, choose the starting model. It can be a null model or a full model. It depends on you. And but the software, so since you do not perform all of these processes manually, you do not need to decide about this. Just learn it. So compute AIC of the current model and try to add the variables, and from the variables that you add each predictor one at a time and fit each candidate model, compute AIC for each, and select the model with the lowest AIC. If the lowest AIC is lower than the current model, keep that variable. And in step 4, try removing variables. So it means that if any included variable should be removed, remove each predictor one at a time. But when you want to decide whether it should be removed or not, just measure the AIC and compute the AIC and find which model is better. And step 5, compare add versus remove. At every step, compare all the candidates' additions and removals and choose the change that reduces AIC the most. And step 6, repeat just, step 3, 4, 5, 3 and 4 until, the AIC cannot be improved further. And the current model is the final selected model. What is AIC? AIC is the ACIC information criterion that is a metric to compare different statistical models. It can answer which model fits the data well without being too complicated. You may ask why we shouldn't complicate the, make the model complicated, because when you add too much variables to your model, you create a model which is overfit and just fit your own data set. And if you want to use it on unseen data, or if you want to generalize it to other data sets, it won't work very well. And the accuracy of your model won't be high. So AIC considers two things at the same time. The first one is goodness of fit, or how well the model explains the data, and the model complexity, or how many predictors or parameters it uses. Here is its formula, and COP presents the number of parameters or complexity. When you add number of parameters, AIC will increase. And L is the likelihood of how well the model fits. So if it increases, the AIC will decrease. We want to reach a lower AIC. So if it is a very good balance between them, and you have a better fit by increasing the parameters, your AIC will reach lower amounts. And again, AIC is only meaningful when you are just comparing the models. Now we want to know how we use, this linear regression in the framework of machine learning. First of all, and we want to know how the model learns. So it tries to first to find the best fitting line by minimizing the prediction errors or least square method. We use this formula. So we want to minimize the difference between the actual observations and the predicted observations and the predicted values. This is the loss function in the linear regression machine learning models. So it calculates the coefficients for the variables that minimize this error. So consider that this is the predicted value and these are the actual values. We want to reduce the sum of these differences. It's the sum of square of these differences. Now, what is the gradient descent and how we use it in linear regression machine learning model? Gradient descent is an optimization technique that we use to train a linear regression model by minimizing the prediction error. It works by starting with random model parameters and repeatedly adjusting them to reduce the difference between predicted and actual values. So here we consider that we have initial coefficients and develop our model according to our initial coefficients. But we understand that our target variable, for example, is placed in this point, and we want to reach the global, minimum or global optimum. So step by step, we just update those coefficients by using the gradient descent and minimizing the loss function in order to reach this optimal point. So gradient descent starts with the random values for a slope and intercept for both beta 0 and the slope, which is the derivative of our loss our the derivative of our loss function according to those coefficients, and calculate the error between predicted and actual values. Find how much each parameter contributes to the error and update the parameters in the direction that reduces the error. Repeat until the error is small as possible. This helps the model find the best fit line for the data. For the model evaluation, we use different metrics. The first one is R squared, which is coefficient of determination. The second one is adjusted R squared. The third one is mean square error. The fourth one is root mean square error. And the final one is mean absolute error. That I will explain all of them to you. The first one is coefficient of determination, or R squared. Is a statistic that indicates how much variation the developed model can explain or capture. It is always in the range of 0 to 1. So if the model can better matches the data, the greater the R squared number will be. If I want to explain the mathematical formula of it, first of all, consider that all the sum of the sum of the square of the sum of square of total is equal to sum of the square of residuals plus the sum of the square of explained. So now, if I want to explain for you the formula of the R square, it presents the ratio of explain sum of a square, to the total sum of a square. It means how our model can explain, the variation or the spread of the data, spread of the data in comparison to the, for our example, the total sum of a square. We use this formula in order to extract the first of all, explain sum of a square, that is a total sum of a square minus residual sum of a square, and then you can reach this formula. And the residual sum of a square is just, computed by sum of the differences, a square of the differences between the actual value and the predicted value. And total sum of the square is the sum of the square of all of the differences between the actual value and the mean value. And what is adjusted R square? Adjusted R square is it is a better metric in comparison to R square. Why? Because it helps us to understand how well does the model explain the data and also penalize unnecessary variables and prevent overfitting and it explains that how our model is generalizable to unseen data. So we use the R square, formula, but just adding the number of observations and number of predictors to add this penalization to, the formula of R adjusted square. So here is the example. Consider that model A just uses two variables and its R square is 0.70, but adjusted R square is 0.68. And model B is use just five variables and reach R square 0.75 and the adjusted R square is 0.66. Which model is better? It's very simple. You consider two variables and you change those two variables to five variables, but your R square just increased by 0.05. It means that, yeah, your R square has increased, but it is not, but probably it is overfit because your adjusted R square presents that the model A has had could present a better fit with less complication. Therefore, model A is better than model B. So it is important that you always consider or adjusted R square in your research problems. Another metric that we use is mean square error, which is the measure of how well a model predicts the data, and it calculates the average of the square differences between actual values and predicted values. What is the difference between mean square error and an R square, R square or R adjusted square? R square and R adjusted square are used to evaluate how your model could explain the variations in the data set, but the mean square error, the mean absolute error, and root mean square error are used to evaluate how far your predictions are from your actual values. Here in the mean square error is used for this purpose. And the mean absolute error is, it measures the average absolute difference between the actual values and the predicted values. And the difference between mean absolute error and mean square error and root mean square error is that Mean square error and root mean square error, it just penalizing these, I mean, difference by adding power to these differences. And so it helps us to find, the outliers better. And especially we emphasize on on the big mistakes in our data. So the root mean square error and the mean square error, the difference between them is just the units. For example, here we just have the units power 2, and for the root mean square error, we have the only the simple units that we have for our metric. So, what are the advantages of linear regression? First of all, it is very simple and interpretable, and second, it is computationally efficient, and especially it works well for linear relationships. And also, it is very easy to implement. However, the limitations is that we should follow all of the assumptions, and all of the assumptions must be satisfied. These are the links that I provided, and I put provided for you and put this slide. These slides for you that you can go ahead and search more and study about the linear regression and different types of it. Thank you so much.